Hello everyone, welcome to this video. In this video we are going to discuss about containers and their internals. Also we are going to create a container or rather a container runtime from scratch, and while in doing so we are going to closely mimic Runc. Not closely but rather loosely mimic Runc. So Runc is one of the most popular container low-level container runtimes out there. Several containerization technologies use Runc under the hood as their container engine. For example, Docker uses Runc. So yep, that's what we are going to do in this video. So let's get started. Cool. So before getting started, let's set some context. So what are containers, right? What is a container? So we know containers are present on Linux, macOS as well as Windows. But what are they? If you search this on the internet, the most classic answer that you will get is containers are lightweight VMs or virtual machines, right? So containers are lightweight virtual machines. But in order to term containers as lightweight, we need to first understand why VMs or traditional virtual machines are heavyweight. So let's try to first understand that. Why are virtual machines considered as heavyweight? Okay, so virtualization using traditional virtual machines involves several layers, right? If I try to explain virtual machines or the concept of virtualization using in the traditional way, so the first layer that we are interested in is the host OS. And this can be any OS. Like let's consider Linux, the Linux OS with the Linux kernel, right? This can be anything like Ubuntu or Arch or anything like that. On top of this, we have on top of this, or rather a part of this layer itself, we have the APIs provided by this host OS, which is the system calls, which are like an interface into the kernel, right? So these are provided by the kernel. On top of this, now we have another layer which is very important in case of traditional virtualization, which is called the hypervisor. And this is something like your VirtualBox, and yep, this is something like your VirtualBox, the Oracle VirtualBox. Another recent example would be Proximox Manager. On top of that, we have the guest OS. The hypervisor allows us to create something called the virtual machine. So virtual machine is something that is created by the hypervisor and managed by this hypervisor, and within the virtual machine there runs our guest OS, and within the guest OS comes our final layer, which is our apps or the application that we want to run. It can be a server program, it can be anything, it can be a desktop as well, right? These two layers are within what we call as a VM, and this VM is managed by hypervisor. So you can spawn multiple VMs on the same host OS, and all those VMs will be using the syscalls or the API provided by the host operating system with the help of this thing called hypervisor, right? The hypervisor is pretty much a bridge between host and guest OS. It has, to be honest, it has multiple functionalities. For example, whenever guest OS would want to perform some action, it will the OS running in this guest OS, let's say that is also, let's say Linux, or let's say you are running Ubuntu, but in this guest OS you are running Fedora. So the guest OS will try to make its own system calls. So these apps will try to access the guest OS's APIs or the interface provided by the guest OS, right? And this guest OS will try to do several things like accessing hardware, accessing the CPU, and all these kind of things. So whenever guest OS makes a call to some hardware, which obviously doesn't exist with the guest OS, but it exists with the host OS. So whenever it makes any such request to access hardware or anything, hypervisor will trap that call and it will translate that call to a call that the host OS understands. So it also acts like a translator. And also it does the work of emulation. So it emulates all the hardware that it requires, and it kind of maps those emulated hardware onto the hardware provided by the actual host OS, right? This can be CPU, memory, and your network devices, right? So the hypervisor has multiple functions. Now, emulation in itself is a slow process. Although with the several developments and the advancement that has happened in emulation, things have grown fast, but still emulation is intrinsically considered to be a slow process, right? And as you can see, there are multiple layers involved in this process. You need a hypervisor, guest OS, and the applications. That's the reason why virtual machines, the traditional virtual machine and traditional virtualization using an hypervisor, is considered to be slow, but it's very secure. However, it's slow. Now Linux, for example, Linux provides something called KVM, which kind of speeds things up. KVM is called the kernel virtual machine that's inbuilt into the Linux OS, the Linux kernel. And what it pretty much does is, let's say if your host OS has got a AMD 64-bit architecture, and your guest OS is also of the same architecture as your host OS, then what KVM will do, it will aid in the emulation work. It will help in mapping the host OS devices, for example the CPU, directly to the guest OS. So the work of the hypervisor to some extent reduces. It's just a very top level overview, or very top level explanation of what KVM does. It's way more complicated than that, but yeah, it's pretty much this KVM helps in speeding up emulation. And also another factor is the boot time. Like in this case, the virtual machines take time to come up, and yeah, overall the guest OS takes time to boot, and which is not very effective when we are talking about cloud environments where we need our services to come up as soon as possible, right? Whenever we are doing a rolling deployment or any kind of deployment, we want our services to come up as soon as possible. Spawning multiple VMs might take a bit more time than containers. Also, the boot time is something which has improved a lot with the newer advancement. Boot time. So one such technology which has reduced boot time of virtual machines to a great extent is something called micro VMs. These are kind of lightweight VMs, and there are entire frameworks for managing micro VMs. One very popular is Firecracker, which was created by AWS, and Firecracker, which is what powers their Lambda systems, like the Lambda functions. But anyways, that's a whole different world. Cool. So now we know why virtual machines or why the traditional virtualization using traditional virtual machines is heavyweight. So now let's come back to containers and how they speed up things and what they do under the hood. Okay, so let's talk about containers now and how they are lightweight. So containers are more of a jailed, isolated environment where you can spawn one or more processes. It's like spawning process in that jail such that it has got no access or no idea of the system-wide entities. For example, a process in a container won't have any idea about the processes that are running inside other containers on the same OS, on the same host OS, or just outside the container in the system itself. Let's consider this is our OS. So this is our OS. Let's say it's some Linux OS like Ubuntu. Cool. So now the first thing that any running OS will have is the init process. So which is like PID1, and this will have an entire process tree. So it can have P1, P2, P3, and so on. Right? It will also have something like the host name. Let's say it's my host, right? And it will have several other things, like it will have network interfaces, it will have mount points, right? Root, maybe /bin, /usr, and things like that. Now let's see what would a container look like. So the container would be a partition, or let's say a box within the same OS without the requirement of any fancy hypervisor or any fancy guest OS. It will be a partition inside the same host OS within which you will be able to spawn process. Now any container that you spawn on a Linux system will have PID1 process. Now this PID1 process need not be an init process. This will be the process which you are starting with, this will be the process with which you are starting the container. So this will be like the top level parent process. This can be something like bin bash. Like let's say you want to jail a bash process, or you want to jail a shell. This will be the parent process, or PID1 inside the container. And then you can in the bash you can, let's say, spawn sleep 10. So in this case this will be PID2. And you can also then spawn something else, like you can spawn a ping process if you have set up network capabilities inside the container. But yeah, then let's say it gets another ID, PID3, and so on. Now this is what a container would look like. This PID1 will have no idea of this PID1. This PID2 will have no idea of this process 2. This is completely a separate, in C++ programming technology, this is completely a separate namespace in itself. Again, this container has its own host name. It can have something like my host 2, and both my host 2 hostname and my host hostname is existing on the same container, but this my host 2 has no clue about existence of this hostname, which is my host. Similarly, it can have its own mount points. It can have its own network virtual interfaces. That's how the resources in the system will be partitioned between the root and this jail. So this is the jailed environment. It can have its own path variable, it can have its own system, it can have its own environment variables. Everything is separate. So now that we know how the container runtime looks like, how the container which gets spawned in Linux looks like, how will these processes, let's say I want to run a Python program inside the container, how would the Python program work? So the idea is, if we want to, let's say, run Python code, all the dependencies that this Python code will need and the Python code's runtime should be present inside the container. So in this case, let's say it will require CPython. It will require CPython to exist inside the container. If you're running bash, the bash binary should be present inside the container. Now the question comes, how are containers then work? How are they implemented? So how container runtime is implemented on a system depends on the system on which it's running. So it will be different for Mac OS, it will be different for Windows, and obviously it will be different for Linux. But how it's implemented in Linux is very, very different from how it's implemented on Linux, or how it's implemented on Windows and Mac OS. On Windows and on Mac OS, containers are created, or container runtime, or the low-level container runtime is implemented using their virtualization technologies, that is the virtualization frameworks that are provided by Windows and Mac OS. So in a way, on Windows and Mac OS, containers are implemented via VMs. So the classic definition or the classic statement that containers are lightweight VMs doesn't fully hold true in case of Windows and Mac OS, right? And these kind of containers, they have a name. They are called VM containers. But how they work on Linux is completely different than this. So on Linux, containers use primarily two very powerful and awesome APIs that the kernel provides, and these are called namespaces and Cgroups. Now, what are namespaces? Namespace is a kernel level API which is used to partition resources in a system such that certain group of processes will see certain resources and others will see it different. Like it is like changing a process's view of the world, or changing the process's view of the system. Like two different. So if I draw an analogy with the real world, let's consider a building floor. Let's say is the first floor of a building, and this building has got two rooms, and this is the door. This is, let's say there are two windows, there is a bed, and let's say there is a table, and this room has got a person, and this room has got another person. Now for this person, the view of the room is this room, and for this person, the view of the room is this room. Now this room has also got a door, this room has also got a door, but this person can only see this door and this person can see this door. Similarly, let's say this room has also got two windows. Now this person can use this window and is completely unaware of this window. Similarly, this person is unaware of this table. Now once they walk out of this window, walk out of this door, they are presented with the same common hallway. So this is like two processes. They are in two different jails. If they escape the jail, they are presented with the same system-wide resources. So in the same way, namespaces provide this feature to isolate or partition resources among different processes. So Linux provides total 5 kind of namespaces. These are the PID namespace. So if you while spawning a process, if you spawn it in a separate PID namespace which is separate from the root PID namespace, it won't be able to see the processes which are in the root namespace, and it can also have its own PID1, it can have its own PID2, and the root namespace can also have its own PID1, PID2. Right? The other is the mount namespace. This is also the first namespace that was created by, or that was provided by Linux. If you spawn a process in a separate mount namespace, it can have its own mount points which are different from that in the system namespace. The other is network namespace. Process in a separate network namespace which is different from the parent or the root network namespace will have its own network devices. It will have no access to parents' networking devices or the parents' interfaces. If you spawn a process in a separate network namespace, it's your responsibility to set up the network infrastructure there as well. Then comes the IPC namespace, or the inter-process communication namespace. This namespace can, if you unshare or if you separate this namespace from the root namespace, then the process here can have its own pipes and other inter-process communication facilities. Then there is user ID namespace. This separates the group IDs, the user IDs, and those kind of things. So the namespace can have its own group of user IDs and group IDs. Actually, there is a sixth one as well, and this is UTS namespace. This is also called the Unix time sharing namespace. This is when you want to separate the hostname of the container from the hostname of the root system. If you spawn a process in a separate UTS namespace, if the process tries to access the hostname, it will get a separate different output than than that of the parent system, right? So these are the 6 namespaces. And then comes something called Cgroups. Let's see what are Cgroups. So Cgroups is a feature or an API by which you can limit how much resources a process can use. For example, you can limit how much memory a process can use. You can limit how many processes a parent process can spawn. So let's say you want a process P1 to use only let's say 1 MB of memory. So you can do this by using Cgroup. Whenever the process's memory consumption exceeds 1 MB, the kernel killer will kill the process. So these kind of things you can do with Cgroup. So Cgroup stands for control groups. And accessing Cgroup is very easy. Like all you need to do is add the path sys fs Cgroups. And let's say if you want to play around with the memory Cgroup, then under memory you create a new directory, let's say a new folder, let's say something like Tinybox, which is the name of the container that we are going to build. And inside Tinybox, the moment you create this folder called Tinybox, you will be presented with multiple files. Let's say Cgroup dot procs memory dot bytes. Using these files are like an interface to the Cgroup infrastructure or Cgroup subsystem. And let's say you want to limit, let's say this is process 10 and you want to limit the memory consumption for process 10. You can simply append the PID of this process, which is 10, in this file. And let's say you want to limit it to 1 MB, you can simply put the limit in this file, and that will set the limit on this process. Similarly, there is one for fork, like how many child processes you want to allow this process to create. What is the maximum number? You can control anything and everything when it comes to resource limits with using Cgroups. So these two are the primary features: namespace and Cgroups, using which you create a container on Linux. And also there is another thing: you need a root file system where you want to jail the process so that the process has a file system to interact with. For that, usually we provide a bundle, and using certain Linux system calls, there are options to do that. We jail the root of the process to that file system. So this and file system, these are the 3 most essential things you need to implement a container from scratch in Linux world. Now let's see how we can make one for ourselves without using any third-party tools, but just Linux interface. Okay, but before starting our container implementation, let's see how we can use namespaces in Linux, right? So for Cgroups, we already know that there is a file system, entire file system dedicated to Cgroup, where we can access the Cgroup infrastructure in kernel by using the files, right? But how do we use the namespaces? So the kernel provides us primarily with 2 calls to separate the namespace of a process, or to spawn process in a separate namespace. One is unshare, and the other one is the clone system call. So the unshare system call is mostly used from within a process to unshare, as the name suggests, to unshare certain namespaces from its parent process. Like for running process gives a call to unshare with certain flags passed. Certain namespaces will be unshared from the parent. Let's have a look at its interface. So if we do man to unshare, this is the unshare call, the library call that is provided. And you see you have a number of flags here. Let's say we want to separate the IPC namespace, so if we can simply pass this clone new IPC, Let's say we want to separate the mount namespace, so we can simply pass clone new ns, and then the mount namespace will be separated. So it's pretty simple, and we have an example program as well provided by the man page to refer to. So yeah, that's pretty simple. Clone system call or clone library call, as I have spoken in one of my earlier videos, it's a library call which is a wrapper over the clone system call, which allows you to spawn processes in Linux. And an added advantage that clone provides you is it allows you to pass certain flags with which you can specify if the new process is to be spawned in a separate namespace. So clone, we can also use clone to do that. In this video, we will go with the unshared way of unsharing namespaces, because that's how Runc seems to do it as per their spec. So yep, in this video we will go with unshare. Cool. So now that we kind of know how containers work and what features of the kernel we are going to use to spawn a container, to create a container, let's start with creating one from scratch. We'll start with a simple main.c. I'll start by declaring some of the include statements that we'll need to use all the libraries that we want to use. So I'll start with some macros. This we need in order to use the sched.h header file, which is used for the unshared syscall. So I'll quickly put in all the header files. Okay, now we'll define one more macro, which will simply help us print any error that occurs. Okay, now that we are done with those, let's start with our main function. So remember, as we mentioned, the main target of this program or this main file would be to create an isolated jail for our processes. So we want to create a jail where we'll spawn a process, and that will be like the PID1 in that jailed isolated environment. Then that PID1 process can spawn further processes. So our main file will be pretty simple. It will simply call our jail function, which will create the jailed environment, and we will define it now. The first thing that the jail function will do is unshare the namespaces that we want from the parent or the parent process, which will be our Linux shell in this case. We will separate all the desired namespaces from our parent process and create new ones for just our jail. So for that, what we'll do is we will call a function called unsharenv. And if that returns a -1, we will simply exit our program with a message, as in to let the users know what failed. Next, we will define our unsharenv function. This will also be pretty simple, but here's where we are going to use the unshared system call. So let's see how we can do it. So first, let's decide on what all namespaces we want to unshare. As of now, I'm going to unshare the new PID namespace. and UTS namespace. Let's stick to these two as of now, just to do a litmus test that namespace unsharing is indeed working. I'll also show how we can check using the procfs file system, how to check if the namespaces have actually got shared. But this will actually show us, like with the UTS namespace shared, we can actually change the hostname of the container, and then we can compare this new hostname with the root hostname. Then I'll call the unshared library call. I'll return this. Okay, so at this point, both the namespaces has been unshared. So at this point, this process has got its own PID and UTS namespace. However, one thing to be noted about the PID namespace created by this unshared process, the calling process, the process which called the unshared syscall, is not moved into the PID namespace. However, if the calling process creates a new child process, that child process is moved into the new PID namespace that got created. So what I mean to say is that the current process, which is the process which called the jail function and the process which called the unshared system call, is not yet in the after this point of time, after the unshared call, it's not yet inside the PID namespace. It's not inside the jail, because that's how the unshared system call is designed. If we spawn a new process now from the calling process, the new child process, that will get moved, or that will get shifted inside the PID namespace. That will be inside the jail. It's a special case for the PID namespace. Otherwise, the namespace has been already separated for UTS. So what we are going to do now is, in the new namespace, in the new UTS namespace, we are going to change the hostname of this environment. And we are not only going to change the hostname, and we'll also set up some environment variables. So let's create function for the same, which will help us set up environment variables, another function to set up the new hostname. So set hostname, we'll take a argument for the hostname, and we will use the set hostname call to change the hostname. By default, the hostname of the new namespace will be inherited from the parent namespace, so it will have the same hostname as the root system or the system on which it's running. So it takes two parameters, the hostname and the length of the hostname string, right? The set, and we'll also set up the environment variables. Let's do that. We'll first clear the existing environment variables so that our system environment variables doesn't interfere with our containers environment, and we will use set env to set up some variables. External we'll also set up the path variable so that when we switch to the new file system, we can access our binaries and normal utilities /usr/bin /usr/bin. Yes, that should be good. Let's get rid of the trailing slashes. Okay, and we will call these two functions from here. Env setup and set hostname, and we shall pass it a hostname Tinybox. Cool. So now what we need to do is create a child process which once spawned will get shifted into the new PID namespace. So for that I'll create a function to handle the child cloning. Let's call it clone process. Child status if clone run. Okay, to invoke clone we also need to decide the amount of memory, the stack memory we want the child process to have. For the stack memory creation part, let's use a function, a custom function which we'll soon define, called stack memory. And also run is the function that will be invoked in the child process. We'll define that soon as well. Let's add the signal 0, and if it returns -1 or -1, we want to exit saying clone is the one that crashed. Okay, and now we just want to wait and repart child process once it exits so that we don't have zombies. So now we have to define two more functions. One is run, another is stack memory. Let's start with stack memory since it's a tiny one. So it will simply return some bytes of memory. We'll give it a stack size of 655p6. Then we malloc that much memory. It's always safe to check if we were able to, if the kernel was allocated that much memory for us. If not, we exit. And also remember, clone wants us to give always the top of the memory, the top of the stack. So we will simply add it. So we'll simply add the stack size with the base address that's returned from malloc. That's it. Now we have our function which returns the starting of our stack memory. We want the child process to spawn a shell such that we can type some commands there and see how our container is behaving. So for that we will use the good old execvp command to spawn a new instance of shell inside the container from this new child process. Again, if you want to know more about clone, how is it different from the existing traditional fork system call, and how we can change the context of a running process using execvp to run a new binary, I have a video on that. You can check that out. I'll put the link in the description. So first let's define the process name that we want to call. It will be shell. The root of the process has not been jailed to a different root. So this bin/bin/sh will be pointing to the shell of our actual system. Let's create the process args that's necessary for execvp. and we are going to print the PID of this process before we spawn the shell. And if everything works out fine, this should be 1, because this is the first process inside our container. Going to spawn a shell via exec vp call. Right, and we'll call get id and finally the exec vp call, proc name and proc args. Remember, exec vp also needs the process name, that is the binary name, as a part of its arguments as well. Cool, I guess we have defined the necessary functions, and now all we need to do is invoke the clone process command. Okay, I guess I've made a typo. It will be clone. Yeah, clone process. Cool. Next, what we'll do is we'll write a tiny makefile so that we don't have to run GCC all the time. So let's create a makefile. It will have a build recipe, a run recipe and a clean recipe. That's it. So when we run this program, what we expect is the jail function will unshare the two namespaces that we want, that is UTS namespace and the PID namespace. Then it should set up some environment variables. It should set up a new host name, and then it should create a new child process, which should be within the new PID namespace. As a result of which, the child process should have PID 1. The child process should be PID 1. Okay, so let's see if it works. First we'll make, and oops, I termed it as Tinybox, but my file name is make, so main. So let's change it to Tinybox because I want to call my container Tinybox. And let's try. Okay, I guess it's a typo again, and it compiled. So if I try to do run, it will give me operation not permitted because unshared requires cap sysadmin capability, so you need to use sudo. And yes, the makefile invoked Tinybox. So in the jail function, we do a successful unshare of PID and UTS namespace, and we also invoked the child function, the child process, and the child process got spawned in the new PID namespace, and hence it got a PID of 1. And let's see what is the host name. It is Tinybox. And what's the host name of our root system? Let's check that as well. Let me zoom it. Yeah, so let's see what's the host name of our root system. That's different. This indicates that the UTS namespace has been successfully shared, and we were able to change the host name in our container without affecting our host system. So what's another way of making sure that the namespaces have been unshared? We can also check this from the proc file system, because every process will have links to the namespaces they are using inside the procfs. But before doing that, I want to also print the PID of the Tinybox program or the Tinybox process. So I can do this here before calling anything inside the jail. PID of Tinybox. Yep. So let's see so this should show us the PID of the Tinybox container as well, as in the parent process, PID of the parent process. So let's exit out of here, and now let's compile it once again and sudo make run, and it's 46639. Cool. So let's go inside procfs. These are all the processes currently in our system. Let's randomly go into any, actually let's spawn a new process. Let me spawn a Python RDPL shell, and let's see. Let's see what process ID it has been assigned. 46729. Okay. So let's check the UTS namespace and the PID namespace of this process. So for that, we'll go inside 46729. Sorry, it's 46. Okay, and then we'll go inside. NS, and we will do -L. So you can see that the UTS namespace points to this UTS, this namespace. So let's copy this, and so this is pretty much the root namespace, because this is the root namespace because it's running this Python shell is running in the root namespace, as in the root system. And now let's see the namespace of this process. You have to do sudo list. Let's see the UTS namespace. As you can see, it is different. Copy. So this is, let's call it tiny UTS, and let's paste it over here, and you can see that these two are different. And if you now check for the PID namespace, so you will see the PID for the Python code, PID for the Python RDPL shell is 836, and the PID for children is 836 as well. So it's the same PID shared by the children as well as the parent. However, if we see here, the PID of the Tinybox parent process, or the PID of the Tinybox process or the Tinybox container process, that's 1836, which is same as the the PID namespace of the Python RDPL shell. But in this case, the PID for children is not same, it's different. So that's because in the unshare call, we invoked the PID, we requested for a new PID namespace, and the child got spawned in a new PID namespace, and that's the reason we are getting its PID, the child's PID, as 1. From the PID perspective, the child is put in a separate namespace, right? But if you compare the other namespaces, for example the network namespace, that should be same between both Tinybox and Python REPL shell. So it's 840 and there is also 840. Even for the IPC namespace it should be same, 1839 1839, right? So now we know that the unshared system call worked and the PID and the UTS namespace has been separated. Okay, let's get rid of these two terminals. If the PID namespace has been separated and the child is in a new namespace, new PID namespace, so does it mean it should not be able to see the PIDs of the other processes in the system? What will PS show in this case? Okay, let's do a PS aux. So this is interesting because we can see all the processes in the system. Although this shell that we are working from, it has been spawned in a new separate PID namespace, yet we can see all the processes that's present on the system. But why so? Does it mean that PID namespace is not working? It's working for sure, otherwise shell wouldn't have received a PID of 1. The fact that it has got a PID of 1, it means it's in a different namespace. The reason we can see all the processes in the system is our file system is still shared with the root file system. The root is still the system root. What I mean to say is, if I go inside /proc and I do ls, I can see all the processes because the proc file system is shared between the system and the container, and the ps aux command simply reads all the processes present in the system from the proc file system. Hence we can see all the files, all the processes present on the system. So to deal with this, what we can do is we can jail the process in the new file system altogether. What effectively it means, it will change the root of the process. So right now the root of the process inside Tinybox is same as the root of any other process in the system. So how we can do that? Okay, so in order to change the root of the process running in our containers, the first thing that we need is a root file system, or in short what we call a rootfs. We need a nice rootfs which will have the basic utilities like it will have a bash binary, it will have the proper folder structure of a root file system like /bin, /usr, /var and those kind of things. And then what we'll do is, using certain Linux calls, we'll change the root of the process which we are spawning inside our container to this new file system bundle or to this new rootfs. So in order to do that, first we need one such rootfs. For this video, I'll go with a very simple one. There is a rootfs there is a mini rootfs which is provided by Apache Linux, and I'm going to use that. So in order to use that, first I'll go to their website. So as you can see, I'm on alpinelinux.org. and this is their mini rootfs releases. I'll grab a tar folder, or I'll grab a tar release and just I'll copy the link. I'll go to terminal, and then what I'll do is curl -0l -output, let's call it rootfs dot tar.gz, and we have our rootfs right now. And now I'll just create a folder called rootfs. Then I'll simply move the rootfs.tar.gs into rootfs. I will untar it now. And it's untarred. I'll now get rid of the tar file. Cool. So now we have our root ready. The root file system ready. Let's see its contents. So if you see, it has a nice folder structure. One cool trick that Alpine Linux does is that it doesn't have the individual binaries for the different Linux utilities like iprout or IPCS, and all the different binaries that we have usually on a Linux file system. Alpine Linux doesn't have those, but all it has is BusyBox, and it simply links all those desired utilities to BusyBox. But yeah, it works perfectly fine. It should work perfectly fine for us. Okay, so now to change the root of the process which we are spawning to this new rootfs, we primarily have two ways to do that, or rather I will be speaking of two ways via which we can do that. One of that, which is the preferred way, or which is the most secured way, is to change the file system, is to completely change the root file system of the running process into this new rootfs using a system call which is called pivot root. So let's quickly see the man page of pivot root. Yep, this is the pivot root system call. Actually, we want the C interface. This is the man page of pivot root, and if you see its description, what it mentions is pivot root changes the root mount in the mount namespace of the calling process. More precisely, it moves the root mount to the directory put old and makes new root the new root mount. The calling process must have the capsysadmin capability, which means we will require sudo in the user namespace, and owns the caller's mount namespace. Okay. So what in short, what pivot root does is it changes the mount point in the root mount point in the mount namespace of the calling process, which also means in this case we will have to separate the mount namespace as well, because we don't want to affect the system's mount namespace. So we will separate the mount namespace as well, and then what pivot root will help us to do is to change the mount point, the root mount point, in the new mount namespace. So another thing that pivot root would expect us to do is provide a path as a subdirectory in the new root, where it will move the current root, the existing root of the process. Its interface is int pivot root, a new root, which will be pretty much our /rootfs, and a path for put old. Now the condition is, which we will see later, put old should be in a subdirectory in the new file system, which is new root. These are the following restrictions that pivot root wants us to respect. New root and put old must be directories. New root and put old must not be on the same mount as the current root, which makes sense because new root will be a new mount point of its own, which pivot root will be creating. Put old must be at or underneath new root, that is, adding some non-negative number of / prefixes to the path name pointed to by old root must yield the same directory as new root. So which means is that old root should be in a subdirectory under new root, so it should be somewhere under rootfs, and these are few other conditions that we must respect in order to use pivot root. So we will quickly see an example. So here is a nice example provided by the Linux man page, where it's trying to create a new pivot root and have BusyBox inside it, and here they have provided us with some example code such that all the restrictions present above will be respected, right? So this is one way of changing the root of a process, by changing the root mount point itself, so that you get a fresh root file system and you have a fresh mount point. And the other way is to not change the file system altogether, but to just jail the process, or to just jail the root of the process into the new file system. This can be provided by a library called chroot or chroot, which people commonly call it. Again, pivot root is the preferred way because it's a more secure way of doing this, achieving what we are trying to achieve, that is changing the mount point altogether so that the process cannot break out of the root. And the other thing that we have is chroot. So what this does is chroot changes the root directory of the calling process to that specified in path. This directory will be used for path names beginning with /. The root directory is inherited by all children of the calling process. Only a privileged process can call chroot. But again, as mentioned, this is not as strong as pivot root. If we read this part, we'll know why. This call changes an ingredient in the path resolution process and does nothing. right? In particular, it is not intended to be used by any kind of security purpose, neither to fully sandbox a process or to restrict file system syscalls. In the past, chroot has been used by daemons to restrict themselves prior to passing paths supplied by untrusted users to system calls such as open. So, one of the most widely used utility of Cgroup is to jail a process inside a new root, such that if a user provides a path such that /x/y/z, that won't affect the host's root path, right? You are not allowing your user input to affect the host's root. Rather, you are running what user has provided in a jailed system, because now once you have called chroot from inside a process and specified a new root, whenever you are using a path with starting with slash, it will always point to the new root and not to the old root. So this is another cool way to jail a processor's root into a new file system, but this doesn't change the mount point. And there are examples on the internet how you can break free of a chroot or a sage root. We will see both these ways. We will start with pivot root, and then also we will see how we can use chroot to achieve a similar effect. So let's start our implementation with pivot root. I'll start with creating a new function called setup root, and I will just add pivot to mention that this method uses pivot root to change the root of the process. The first thing which we need is a location of the new root, which will be our rootfs. The next thing which we need is the location where pivot root will transfer the current root, and we'll call it old root fs. And we will create the full path of the old root in this path variable. Okay, so the first thing we need to make sure is that the new root and its parent mount doesn't have shared propagation. This would cause pivot root to return an error and prevent propagation of mount events to the initial mount namespace. So this is one of the restrictions that we need to respect when using pivot root. We can achieve this by using the mount call. So let's do that. If mount null / null this gives us 1, we error out saying file system is private. Okay, so the next thing that we need to make sure is the new root is a mount point. Let's check that as well. New root null. So by the way, these conditions are exactly same as what the man page provides. We don't have to do anything different here. Next, we will create the absolute path where the old root, or which is also the current root, is going to be moved once the new root file system becomes the mount point. So let's create that. For that, we will simply use snprintf to create a nice formatted path. We won't use slash because slash is already present in the old root path, put old root. So new and we will create a directory for this path. We will error out if mkdir fails. Next, we will call pivot root. And fun thing, pivot root is not a library call. I mean, glibc doesn't provide a library call or library wrapper for pivot root. So this is undefined as of now. We will define it very soon. And pivot root will simply take two parameters, new root and the old root path. And if that returns us -1 or -1, we will exit. Cool. The next part is very important. The pivot root call will not always change the current working directory, although it will change the root definition of the process, because the root mount point is obviously changing, but it won't change the current working directory, which means if the process's current working directory is not in the new FS, the process will start by being outside the jail and not in the jail. So what we need to do is, to be on the safe side, what we need to do is, after we have called pivot root, we will change the directory, we will change the working directory of the process, of the spawned process, to / or to root, and that root will be our new root FS. So from this point onwards, after pivot root, any path that starts with any absolute path which starts with / will always start with the new root and not the existing host's root. So let's use chdr to do that. And finally, inside this container, we will unmount or umount the old root. And once the old root, or which is the present current root, has been umounted, we will get rid of the folder because we don't need it anymore. Cool, simple enough. We are not doing anything else apart from what has been already mentioned in the man page of pivot root in order to invoke pivot root without any potential issue. Cool, so let's once again see what all we did. The first two lines makes sure that we are respecting the restrictions put forward by pivot root. One related to shared propagation and another makes sure that new root is a mount point. Then we create the absolute path for where we are going to put the old root, or which is the current root, which will become the old root after calling pivot root. We create the path. Next we call the pivot root, pass it the new root and the old root path, and then we change the current working directory to the new root, and finally we unmount or umount the old root path and we get rid of that directory. Okay, now what we need to do is we need to create the pivot root function. We'll take new root and we will take old root. That's it. And then we will invoke the syscall using the syscall library call. will provide the new root and the old root, and I believe we missed one header file. Yep, we need sys call.h, and that should resolve sys pivot. Okay, that's the pivot root tiny custom function. And now what we are going to do is we are going to, just after setting up our environment, we are going to call setup root pivot, right? So what this should do is, as I already mentioned multiple times, this should change our current root file system and the root of the process. Okay, so let's see now if it works as expected. So let's build and then run it. Okay, let's started our shell, and let's now do a PS, and we can't see any process now because our proc file system is gone. This is because we are completely in a new file system now, the Alpine Linux file system which we just downloaded. And now if we go to bin and we do ls-l, so it's no more our root or no more our host bin, but it's the new bin where everything is symlinking to BusyBox. Awesome. Okay, but one thing I forgot to do is to unshare the mount namespace as well. So let's quickly do that. Without this, our system might behave in weird ways. So let's quickly add clone new ns, and this will unshare the mount namespace as well. So let's once again try to build. And yep, PS shows nothing, and exit. Okay, however, the fact that now PS is not showing anything is not something that we want. So what we ideally want when typing PS is to actually show the processes that's present inside our container, or that is present inside our isolated environment. So in order to do that, from inside our container or from inside our isolated environment, we will have to mount the proc file system. So let's quickly do that. So for that, I'll create a new function called, I'll create it just above run because we'll be calling it from inside run. And the function that I'll be creating is map file systems. Although we'll be mapping only the proc file system, but anyways we'll just call it map file systems, and within that we will mount proc. So source will be the proc of our new file system, destination will be select proc, which is within the new file system, and type will be proc 0 and 0. And then we'll just check if mount worked as expected. If not, we will exit, stating mount errored out. This we will call from our run function. So run is called just when, so run is the method which is called by our the clone method or the clone system call. When the run is being called, it means it's from within a new process in the new environment. So let's call map file systems from here. And since we are mapping the file system, when the work of the container is done or when the process exits, we need to unmount the procfs as well. Let's do that as well. and for that I will be creating here itself a function for unmapping the file system. And for that what I'll do is umount/proc. That's it, and this we can call after cloning our new process. So inside clone process, just after we invoke run, we call map file systems, and what map file system does is it mounts proc inside the container, inside this isolated environment that we are creating. And after that, after the process is done with its work, we call unmap file systems, which simply unmounts/proc or umount/proc. Now let's build it and then run it. Cool. And now if I do ps, yep, I can see two processes. One is ps, the one which we just executed, and another is our shell, which is pid1. And if I do psaux, it's the same two processes it's showing. So yep, now we can view the processes within our new container, and if we try to see inside proc, we will see just these two processes. And if we see inside /proc, we no more see the processes of our host system. We have successfully mounted a new proc inside the container. Now the other thing that I mentioned earlier is that the other way to separate our file system, or the other way to not separate our file system, but the other way to jail our process into a new root file system, or change the root of the process inside our container, is using the chroot command. So let's see an example, or let's also try to see how we can achieve this using the chroot command. For that, I'll create a new method which is called setup root. The old one was setup root pivot, and this will be setup root chroot. And inside that, what I'm going to do is I'm going to call the chroot command, and I will say change root to rootfs, and then it's always better to change the current working directory to /. Again, see how this does not involve mounting or unmounting any file system or anything, because in this case we are not separating the file system. It's the same old, we are not changing the root mount point, right? We are not changing the root mount point. The root mount point remains the same. We are just changing the root of the processes that get spawned inside the container to our new file system, which is rootfs. So we are not changing the mount points. The mount points remain same as that of the host. We are just changing the root of the process. So let's call this instead of this. Exit from our container, we build it, and sudo make run, and it has got the same effect. We do psaux, that's it. It's showing only the processes running in our container. If we go inside proc is mounted, and we can't see the host processes, right? So yeah, that's how we can use pivot root and chroot to achieve the same effect as changing the root of the process. But in one case, only in the case of chroot, as the name suggests, it simply changes the root of the process. But in case of pivot root, we are completely changing the file system as well as the mount points, the root mount point. Okay, so now that we have a basic process isolation in place and a basic jailed environment is in place, now we'll look at how to limit resources. So that is, we will try to limit the resources consumed by our container process. Before moving on to that, let's switch back to pivot root. Okay, so in order to put resource limits, we will use cgroup, and the interface that the Linux kernel provides us to use cgroups is a typical simple file system. So if we go inside /sys fs cgroup, we can see the various cgroup directories present over here. To get started with, first thing that we'll try to limit is the number of child processes that our container process can spawn. Let's say we will limit it to 5. So if our container process, as in the process that creates the jailed environment and everything, that core process, if it tries to call fork more than 5 times, right, then it won't be able to do so. It will fail. That is how we will limit the number of PIDs that the parent process is gonna create. So in order to do that, we will need to go inside PIDs, and inside PIDs we will create a new folder over here. Let's say we will call it Tinybox, and inside Tinybox once we create a folder inside Tinybox, let me give an example with some other folder name. Let's say we will call it sample group. So I need to be root, so let's create sample group, and if I go inside sample group, so see, these files are already created by the kernel for me. So these files are kind of interface into the cgroup infrastructure or the cgroup subsystem provided by the kernel. So what we need to do is, right now if we see cgroup.procs, we'll see it's empty. Whatever process on which we want to impose this limitation, that process's PID should be fed into this file, that is cgroup.procs. What it essentially means is that limitation, like whatever PID we put into cgroup.procs, not only this resource limit of child creation will be imposed on that process, but it will be recursively imposed on all the children created by that process. So if we put PID x and PID x gives rise to PID y, so this limit will be imposed on PID y as well. Again, if y spawns z, then the PID limitation or the process creation limitation will be imposed on z as well. And another file that we'll use in this example is pids.max. We'll put a number here saying that how many child processes the parent process can create. And finally, we'll also put the PID in notify on release. If you put a PID here, it's just a notification to the kernel when the process ends, saying that the process on which the resource limits were imposed has finished and the kernel can do its cleanup. So these 3 files will be primarily be using. So yeah, let's get started. Okay, one correction, it's not the PID that will write on notify on release. We saw that notify on release had 0, so we'll just make it 1. 1 means the kernel will get a notification once the process exits and it will clean up the resources. Okay, so now let's start with this. So first we'll create our subfolder, which we'll create after the name of our container, which is Tinybox. We'll call it Tinybox container maybe. So for that, I'll first start with creating a function called, let's create it up here. We'll call it limit processes. And first let's define a cgroup folder. Cgroup PIDs as we just now mentioned. Then let's name it Tinybox container. Yep. Then we will create a PIDs max. This will contain the final. So remember how we need to manipulate 3 files. We will just allocate 3 variables for those 3 paths, which we will dynamically create by concatenating. Like there is nothing that important here. It's just C string manipulation. Maybe there's a better way to do this, but I'll just go ahead with this way. So I'll just create 3 variables for the 3 files: PID max, procs, and notify on release. So next I'll create our cgroup folder, which is Tinybox container. and I will do my WUSR, user can read and write. Then I'll get the process of the PID of the process on which we want to impose the limits, which is the PID of the current process. And next I'll just create PID str, and it will just hold the string version of PID. So let's do that. I will do char star, and I'll just randomly allocate 12 bytes. I'm just assuming the PIDs that will be dealing with won't be more than 12 bytes in string format. So they won't be more than 12 bytes in string format, or rather it won't be more than 12 digits. We'll use sprintf here. Sprintf is quite a handy library call to create formatted string and store them in a variable. So I'll just do now we have a string version of the PID stored in PID str. And now what we are doing now is, let's assume we have a hypothetical function called write rule, which will write these things into our file. Rather than opening and closing individual file, we'll consider we have a function called write rule. And actually before that, let's create our function which will concat two strings. This will concat the individual file name with the total absolute path, right? So let's do that. Concat paths char star container. So this is the container string where the concatenation of first string and second string will reside. This is str string A and this is strb. Again, there can be a better way to do this. I'm just following this procedure, and then I'll simply do strcpy container stra. Note, we could have simply taken the first string and we could have simply appended the second string to the first string as well. As you wish, you are free to change this part. Then I'm going to concat strb with container, and I will simply return container. Okay, and next we will create another function, and this function will actually write the stuff into the individual files. So let's do that. Write rule star path. This is the path of the file, and const char star val. This is the value that we are going to write, and we'll do integer file pointer equal to open path. We don't want to read, we just want to write. So we'll do 0 O only and O append just in case, and we'll use the write system call, or rather write system calls library wrapper, which is write, and we will just write val and we will close the file. That's it. So we opened the file, we wrote the value, and we closed it, and now it will all make sense, since now we can simply call write rule, and what write rule will take is a path and a value. So the path we will create using concat paths. We'll do first, let's write down into the pids.max file how many max processes we want our parent process to create, after which it should recursively put the resource limit on the parent and its corresponding children. So we'll do cgroup folder So again, PIDs max is the container, cgroup folder is the first string, and next will be PIDs.max. So this is the file where we are going to write, and our value will be 5 in string. Next we will write to notify on release, write rule concat paths notify on release cgroup folder, and the file's name is notify on release, right? And the value we are going to write is 1, and the last file that we are going to write, that is to procs cgroup folder. Name of the file, as we saw, is cgroup.procs, and we will write to this PID str. We have written to all the 3 correct files, hopefully. PIDs.max, notify on release, and cgroup.procs. Hopefully I have spelled them correctly, and yep, that's it. And now what we'll do is we will call this, we will call limit processes just after our environment unsharing has been done. So we'll just limit it at the beginning only, so that nothing is missed. Okay, let's do one thing. Let's clear it. Oh, it's already clear. Let's go into our Tinybox root folder, and let's split the screen. Let's zoom it. I hope that's enough. And now what we'll do is we will make, and we will make run. Okay, and now we will, here what we'll do is we'll go inside sys fs cgroup, and inside that we'll go inside PIDs, and inside PIDs, here we go, our Tinybox container has been created. Permission denied, that's fine because it was created as root, so I'll just switch to root. So now I can enter here, and let's see. Let's first check PIDs.max. Okay. Procs. Okay, looks like something is not working. We did our limit processes here. We did it here. This got created, and then we concatenated the paths. We are sending it the cgroup folder. Okay, I know what's the issue. We missed a trailing slash, and I believe that's why I should have done error handling over here, which I didn't do. I'm pretty sure this open would have failed, but anyways. Okay, let's build it once again. Do a sudo make run. Let's get inside here, and then let's pull it up once, and then let's do a PIDs.max. We have got 5, and let's do cgroups dot procs, and we have got 9226 and 9227. Why we have got two processes, 9226 and 9227? So 9226 is the, so if you see, we called limit processes here. So this is the process, this main process. Like this process is basically the Tinybox process, which creates the isolated environment. When we are doing sudo make run, the process that gets created from there, we are calling limit process. That is the PID of, so that process's PID is 9226. So we can check this, right? We can do a aux Tinybox, and yep, that's 9226, right? And so this 9226 process, this creates another process, which is the process which is spawned inside our unshared environment, and which has got the PID of 1. So that is 9227, but we didn't separately add 9227 inside cgroup.procs, right? Why is it getting added over here? That's because, as I mentioned, whenever a child process will be created by the parent process, or that has already been added to cgroup.procs, its children will also keep getting added to cgroup.procs, right? So that's the fun thing. That's how the recursive resource limit is imposed. Now the other thing we can do is we can cat pids.current, and we'll see, like already under our monitoring criteria, that is the processes we are monitoring for PID resource limit imposition, like the child creation limit criteria for which we are monitoring, we will already see there are already two processes for which we are monitoring. According to our criteria, two processes has already been spawned out of 5 processes. How is that so? That's because of the parent container process, that is our Tinybox process, and the PID1 process, that the parent container process spawned inside the new PID namespace. This process, this entire process of PID limitation, it also considers the parent process as one of the 5 processes that we can spawn. So then technically we should be able to spawn 3 more processes in the container from PID1, and after that it should prevent us from spawning any new process. So let's see. So for that, what we'll do is we'll do sleep 10 and we will run it asynchronously. So sleep will spawn a different process which will simply sleep for 10 seconds, but the process will need to be forked, and it will be a child process of PID1. So 1, 2, 3, and the 4th time it can't fork, right? So that's how we are imposing process creation limit on top of the parent process and its first child. So in total, there are 5 processes that could allow me to create the parent process, its first child, which is PID1, and 3 more processes. So that's an example of how we can limit resources, and we can limit how many children a process can spawn inside the container. Okay, so now we know how to put restriction on number of processes that can be created, or rather a number of fork calls that a process can invoke. Now in this next example, we'll see how to limit the amount of memory that a process can use. Again, for this we will use the cgroup, but we will use the memory subsystem of the cgroup file tree. So let's see how we can do that. So for that, the file path where we will be writing our memory limit is something like this. We'll go to sys fs cgroups as usual, and then memory, right? And we already had our previous Tinybox container, so if we go inside that, what we'll see is this various file, and it's also pretty much similar to the process restriction. So we'll have a file called cgroup.procs where we want to put in the PID of the process on which we want to impose the memory restriction. The other file which we will use is memory.limit in bytes. Here we will feed in the number of bytes to which we want to limit memory consumption for that process, and the other is notify on release, which will help the kernel to clean up the resources once the process exits. Okay, so yeah, let's get started. Let's get out of root, go inside Tinybox, and cool. What we will do now is we'll create another such function for limiting memory this time. Let's do that. It will be pretty similar to limit processes, and we will do limit memory. We can simply copy this part. This will be, I'll name it instead of PID's max, it will be limit in bytes. This will be limit in bytes, and yeah, procs will be same. And once again we will have this thing converting our PID into a string. Okay, let's first create the PID str variable. Str equal to char star malloc 12, and we've got, we'll do a get PID here, and yeah, it will be memory. And the next thing we'll do is we'll create this path, which is Tinybox container. Let me adjust my mic once. Yeah, that is Tinybox container. And then we will have, after this is done, we will simply copy these 3 write rules and we will paste it here. And instead of PID's max, now we have limit in bytes, which is this. All good. And oops, this will be memory dot limit in bytes. Limit in bytes, right? And we will put it to somewhere around, let's say 400 KB, right? We'll put it on something to 400 KB, so which is 1024 bytes into 400. That's 4096. 409600. Yep, we wrote 3 rules. One is in memory dot limit in bytes. We set it to 409600. We set notify. We set 1 inside notify on release, and we dump our PID, the container processes PID, in cgroup.procs, and that's it. And now, instead of calling these 2 processes separately, let's create a tiny function called configure cgroups, or configure, let's say, in resource limits, and we will call limit processes and limit memory, right? And then we will call this function here. So now resource limits will call limit processes and limit memory. Limit memory is the one which we just now defined. Now let's see if it works. First, what we'll do is we'll make it, and then sudo make run. First, let's see if our, so we already have seen this, wherein this will do a fork issue, fork error. Also, first let's see if we have got our folder created. Cgroup memory, we have got Tinybox container. Let's switch to root. Tinybox container, and let's see the cgroup.procs. Yup. Again, this limit is also imposed recursively. So the child processes created by the parent process will also have the memory limit imposition. And then let's see memory dot limit in byte. Okay, so something went wrong. This number shouldn't be this big. Let's see what happened. So I made a typo. it should be this. Okay, let's cancel this, remake, sudo make run, and yep, let's see. So it would clear, but now let's type a command. Let's type ls. You see it's taking so much longer because it has to do everything within that memory limit. It would do an ls. Now let's do something fun. Let's do this. Let's echo a string inside a file called a.txt. It worked. Now what we'll do is we'll try to allocate lots of memory sufficient to overrun 4 KB and 400 KB, and for that let's create a big file, right? So what we'll do is cat a.txt, and we'll put it to a.txt, and it got killed. I didn't even have to create a huge file in order to allocate. So what I wanted to do was I would create a huge file and then I would try to read it, but even I didn't even have to do that, like, because the memory limit was so less, like even running a few usual commands overran the memory. But how do we know that it got killed because of memory? Now let's check that. Let's get out of root and let's do something. I'll do a tail -f on var log current.log, and let's clear it up. Let's do a sudo make run, and let's once again do some funny thing. Let's do echo away a.txt, and I'll do a.txt and try to append it to a.txt, and let's see. And we get this in our current.log, which is memory cgroup out of memory killed process 32168. Our killer got invoked, kernel's killer got invoked, and it killed this container process because it tried to consume more memory than it was supposed to, or than it was allowed to. So the process was 32168. Let's match this process with the process we printed in we put in the cgroup file. So cgroup, so it's 32168, and we do sudo su, and then we go inside tiny container and we try to do cgroup dot procs. Okay, now we can't see that because the container is dead. So what we can do, we can start it once again and let's see. So it's 32305 and 32306. Okay, and then let's again try to tail our logs. So remember, it's 32305 and 32306, and let's do what we did earlier. We echo something to a file. Again, like, this need not be the way to make it run out of memory. You can do any other random things, like whatever takes more than 400 KB, it will invoke killer and the container will get killed. So it need not be this way of creating a file and writing to that file. It can be, if you find any other way to allocate, maybe creating an array in bash, that will also work. And a.txt, and I write it to a.txt, and it was 32305, 32306, and let's try this. And our killer got invoked and it killed 32305, which is the first process, 32305, which is our container process. and 32306 must be its child, which is the PID1 process in the new namespaces that we created. So the parent process, the container process, got killed, which is 32305, right? So that's how we can put another limit, another kind of limit, which is like the memory limit. Similar to this, you can put other limits as well. You can put CPU limits, you can put block device access limits, PID we have already seen, and those kind of things. So yeah, it's pretty cool how you can put resource limits on using Cgroups, and this is what all the containerization technologies use in the real world, like for example Docker, Linux containers, and all those kind of containerization technologies. So that's pretty much it. I'll put all these codes in my GitHub and I'll share the link in the description of this video. Hope you all enjoyed this video. I just wanted to show what is the magic that happens inside a container, like how containers work on Linux, what is the concept of namespaces, Cgroups, how you can create your own container or your own jailed isolated environment from scratch. So yep, thanks for watching and see you all next time.